Hi everybody. I want to make sure that you had some tips for studying for exam 2. First thing you want to do is make sure you familiarize yourself with the formula sheet. The first couple rows have formulas from the first exam. The remaining formulas are covering things that are everything since the first exam, and that's what we'll focus on for exam 2. So for example, we have z-scores. We have formulas that will take a z-score and transform it back into a raw score. We have z-scores for when we're dealing with sample means and sample proportions. We can compute a margin of error for sample means or sample proportions. We can compute the sample size when we're dealing with sample means or sample proportions. We can compute confidence intervals with sample means and sample proportions. So one thing you'll notice is that there's a lot of redundancy in the formula sheet. So although it looks like we have lots of formulas, in general, we have each formula in two different situations, dealing with means when we have quantitative data and dealing with proportions when we have non-quantitative data. So that might help you simplify things. Most of the chapters are broken down that way as well. We learn some new concept, then we learn how to apply it to means, and then we learn how to apply it to proportions. So be sure that you're familiar with the formula sheet. If you're not going to be able to identify what the symbols represent, like N represents a sample size, E represents error, S represents a standard deviation, if you're not able to do that, then you're going to run into some trouble. So of course, be sure that you can identify everything on the formula sheet. All right, let me focus on a couple other things now. Here are major points to focus on. We started talking about what it means to have statistically significant results. And of course, when we talk about statistically significant results, it essentially means it's very unlikely to find those results by chance. Be sure you understand that basic concept, and be sure you understand about significance levels, like when we say that something is significant at the 0.05 level, 0.01 level, or 0.001 level. We talked a lot about probability. There were three main ways for us to view probability. One was in terms of relative frequencies. One was in terms of theoretical probabilities, and another was in terms of subjective probabilities, which are essentially just estimates based on our intuition, so we didn't talk too much about this. Be sure that you can distinguish between these three, and be sure that you can compute probabilities based on these two types, relative frequencies and theoretical probabilities. So for example, when we talked about relative frequencies, we had this basic formula, and then we applied it to several examples. When we talked about theoretical probabilities, we had the same basic formula in general, but we talked about counting the total number of possible outcomes. So look at those examples and be sure that you can compute probabilities using this theoretical method. We talked a little bit about counting those outcomes, and we talked about some easy methods as well when the events are assumed to be independent. So be sure that you're familiar with the shortcuts that we've learned also. This was an example that put together theoretical probabilities with the shortcut that we learned for determining the probability of winning a lottery. I'd be pretty familiar with this type of example if I were you, because you might see an example like that on the exam. We talked about 3 different rules of probability. Go over those and make sure you're familiar with the basic reasoning. The reason why we focus so much on probability, of course, is because inferential statistics speaks the language of probability. When we say we have statistically significant results, it's because we're saying the results are unlikely, which is a probability, to occur by chance. Well, as we were talking about probabilities, we talked a little bit about the law of large numbers, also known as the law of averages. Be sure you understand what that law means and what it's trying to teach us, because I might ask you to explain it. Same thing with the gambler's fallacy. What does it mean when someone is making the gambler's fallacy? Be sure that you can explain something like that as well. You might need to on the exam. Expected values were an interesting thing that we talked about as well. So by coupling probabilities with some basic computations, we were able to figure out essentially the expected value of some type of event, like purchasing a lottery ticket. And we went through this example of purchasing a lottery ticket where there are various probabilities associated with winning various amounts of money. And we're able to compute that overall, you lose about 64 cents for every dollar that you spend. You should be able to compute these basic expected values. And this is a really good example to study from. We then started talking about normal distributions, and the main reason we started talking about normal distributions and probability was because most of our data we can assume to be normally distributed, and if we can figure out the area underneath this curve associated with various scores, then we can figure out probability. Probability equals the area underneath the normal curve associated with particular values. So go over those notes and be sure you understand that basic point that I just made. That's why we keep looking at these distributions, because then we can compute probabilities. So when we started to talk about this in more detail, we discussed the empirical rule, which is also known as that 68, 95, 99.7% rule. So we were able to interpret results based on that rule when we had a normal distribution of data. This was a good example right here with SAT scores. So you might see something like this on the exam too. Really smart to look at these examples and be sure to understand them. We then started looking at z-scores. So z-scores helped us compute probability for any measure because we were able to take that measure and then convert it into a z-score. So anything that we can measure, we can convert into a z-score, and once we have that z-score, we're able to look up some probabilities. So here's a good example of that. We had IQ scores. We were able to transform those IQ scores into z-scores and then compute the probability of scoring less than 85, for example, or what's the probability of scoring greater than 125. If we transformed that score into a z-score, we could then look up that value and figure out how much area was left in this curve, how much area was left in this region. That then told us the probability of scoring in that region. Area equals probability. So be sure you look at these examples. Of course, anything we compute in class, you'll compute on the exam. That's the good news. All I can do is give you different numbers. As long as you know how to use the basic formula and interpret the results, you'll be fine. So you already know exactly what to expect on the exam. Anything we computed in class, we will be computing on the exam. So here's another example. We then determined that if we were able to find a z-score, we can then use that information along with a mean and a standard deviation to transform that z-score back into a raw score. So look at those examples. I'm sure there will be at least one question on the exam like that. We then started to take our discussion not from individual data points, but to sample means. And that's because research studies typically measure many people, and then we compute a mean, a group mean, or a sample proportion. So central limit theorem discussed the distribution of sample means, and here are some properties of that distribution of sample means. You should be familiar with those properties. Once we are able to understand the distribution of sample means, we're able to take our discussion of z-scores from individual level data, when we are dealing with just one data point and then computing a probability, to situations in which we are dealing with sample means. So for example, we had data from an entire school, and then we computed a mean, and we're able to figure out probabilities associated with it. So go through those examples and make sure you understand the difference. We're using z, but the formula changes just a little bit. So here's the z formula when we're dealing with individual scores, and you should always look for the dead giveaways. X equals an individual score. That's why we see that in this equation. This sigma equals the standard deviation for individual scores. That's why we see it in this equation. And here I'm asking about one student, an individual score. But now look at this example. Here we're talking about an entire school, and we're dealing with a sample mean. And here in the formula you see x bar. It's a sample mean. And now we're not dealing with sigma anymore, but sigma with a little sub x bar. And you might recall that that's the standard error of the mean. Well, that's the standard deviation for the distribution of sample means. So as long as we understand those basic concepts, we'll always know what formulas to use. We can just look at the example and pair it with what's in the formula. We started computing confidence intervals then. So we were able to use sample means to learn about a population mean with great confidence. The probability was 0.95 in most of these examples. So we had this basic setup where we took our sample mean and we added the margin of error and we subtracted the margin of error so that we were able to find an interval of values, of range of values that was 95% likely to include the true population mean. Well, we put that together into basic formulas like this. So we need to understand that E represents the margin of error. We use this basic formula for it, and then we're adding and subtracting that value to and from the sample mean. So of course you're going to see some examples like that on the exam. Also in that particular section, we talked about how we could compute a sample size to make sure that we would have a particular margin of error. Well, here's the formula for it. And again, if we know what n represents, it's easy to figure out what formula to use to answer those types of questions. Now, of course, that discussion that we had of confidence intervals also extended to sample proportions. So here we see the exact same type of situation. We computed a sample proportion. We wanted to figure out what the true population proportion was. So what we did was we constructed a confidence interval where we added the margin of error, we subtracted the margin of error, and then we found an interval of values that was 95% likely to include the true population proportion. And of course, in that situation as well, we computed the confidence intervals on our own using the formulas. Again, E would represent the error, the margin of error, and you would look at the formula and you would recognize that it's a formula dealing with proportions because you would see P's with a little hat on them. Those are sample proportions. So again, be sure you're really familiar with that formula sheet. That formula sheet will tell you exactly what you need to compute. And then of course also, when we were dealing with margin of error and we were dealing with sample proportions, we would have a formula involved for that. We then put everything together and we started talking about hypothesis testing. It was a more formal procedure for learning about true population mean and true population proportion values. We wanted to see if we had statistically significant results. So we spent some time talking about how those tests are structured and set up. So for example, we knew that we had right-tailed, left-tailed, and two-tailed tests. Be sure that you can set up a test for a right-tail or a left-tail type of hypothesis or a two-tailed hypothesis test. And be sure that you could interpret the results whether we rejected the null hypothesis or whether we retained the null hypothesis. I will provide for you on the formula sheet the critical values that we will use in those hypothesis tests, whether we're using an alpha level of 0.05 or 0.01. You'll see this right on your formula sheet. So this shows those critical values, those rejection zones for a one-tailed test. We put everything together and we did a one-tailed hypothesis test. You should look through these to make sure that you understand them, each step along the way. You're going to see an example just like this on the exam, and all I can do is give you another example. So you're going to still go through the exact same steps, it's just going to be another scenario, so you can completely prepare for this. We also talked about those two-tailed tests, and here you can see that I added a row to this little table. It shows the critical values when we're using an alpha of 0.05 and the critical values when we're using an alpha of 0.01 for these two-tailed tests. So you will see that on your formula sheet. Now we have these critical regions or rejection zones on two tails. So you might recall I mentioned that these tests are very common. These are the most likely significance tests that you will find, a two-tailed type of test. And that's because theoretically, if the results can go in either direction, then most people will do a two-tailed test, where we might find, for example, that a drug significantly helped people, but it's theoretically possible it could significantly harm people. So we leave open the possibility that we might find statistically significant results in either direction. So these two-tailed tests, they're very common. And here's an example of one of the two-tailed tests. Again, you should look through it and be sure you understand how it works, how it's set up. You know that you're going to see one on the exam. All I'm going to do is give you another type of scenario and you're going to plug everything in. They all work essentially the same way. So be sure you completely understand one example. If you do, you'll be able to apply it to almost any example. So if you have questions, of course, be sure to let me know. Here's an example of a hypothesis test dealing with proportions. So of course, anything that we learned with means, like in this example right here, we can also apply to proportions. We just have to make sure we use the appropriate formulas. And again, the big giveaway here would be we'd be looking at this sample proportion in the formula as opposed to this formula where we're dealing with a sample mean. If I'm referencing a sample mean in the basic information for the example, then the formula, of course, is going to need to reference a sample mean. In this particular formula, we're dealing with the number of votes that someone gets. There we need to compute the proportion of votes that the person gets. So we would know that we're dealing with sample proportions, and the formulas that we use would need to have sample proportions listed in them. So I'm trying to help you understand how to pair information to a formula that you need to use to answer a question about that information. All right, everybody, that's about it. If you have questions about any of this stuff, be sure to let me know. Good luck on the exam. For now, that is all.